So, hello everyone, my name is Georgi, and in this talk we're going to explore what Elixir offers as a language and why you might want to try it out. We've heard a little bit about Elixir throughout some of the talks already, but we're going to dive in a little bit more specifically into Elixir and see what it actually is. So, a few words about me. I'm enthusiastic about programming, and I have been in the professional space for around 7 years now. I enjoy sports, and I have a cute cat, but I'm pretty sure we are not here to listen about me, but probably you're here to listen about some Elixir. And first, we have to see what is Elixir. And Elixir has this explanation that it's a functional programming language built for large-scale, highly available, distributable, fault-tolerant applications. And that's a mouthful. And although it sounds like these features are coming from Elixir, they're actually inherited from the virtual machine, or Beam. Ricard actually mentioned it a little bit in his talk. So essentially, Beam is the ecosystem that was created to support this feature set, developed back in 1986 by the telecom company Ericsson. There are a few languages that support this feature set, such as Elixir, Erlang, and we heard about purecode. But now, in general terms, Elixir aims to be the model language on the Beam. So first, let's look at the syntax. Although inherently unimportant, I know some people care about it. And we briefly saw some Elixir syntax in Ricard's talk. But as maybe you've seen, it's kind of straightforward and easy to understand. Here we have a module that defines the function which calculates the sum of all the elements in a list. In the first definition, we pattern match on an empty list, which marks the end of our recursion by returning 0. In the second definition, we pattern match on the head and tail of a list. And in the body, we add the head to the recursive call of the sum function over the tail. Here in the pattern match, we actually saw this similar with Simon Thompson, but there it was X and X's. But it's a really similar idea here in Elixir. The syntax is a little bit different, but the idea is the same. This matching of arguments is probably, as you have heard already a couple of times, pattern matching. So in most other languages, the equal sign is treated as usually the assignment operator. On the left side, we put the variable, and on the right side, we put some value or expression that resolves to a value. Elixir treats the equal sign in a completely different way. In Elixir, the equal sign is treated, or even called, the match operator. It attempts to match the expression or value that we have on the right-hand side to the pattern that we have on the left-hand side. And patterns can be as strict or as vague as we need them to be. In this first example, the pattern expects the value on the right to be a 3-element size list where the values are 1, 2, and 3. And this is as strict as it gets, and we can easily see that it would match because it's exactly the same as the value itself. And strict patterns are usually used to verify that the data is exactly as we expect it to be. A non-strict pattern allows you to verify the shape of the data and give you the availability to bind various variables values. So here, first we're binding the first variable to the variable first. We don't care about what the second value of the list is, so we use an underscore, which is treated as a placeholder. Anything there can match. And finally, we expect the third element to be the number 3. And this matches as well. Since we bound the variable first to the first element of the list, now this pattern is valid as well, because the first the variable first holds the value 1. Essentially, patterns allow you to specify your expectations of the data, and matching the pattern verifies that your expectation has been correct. And if a pattern match fails, Elixir throws a runtime exception. So then, what could we do in order to attempt multiple possible patterns? Well, there are multiple ways to go about it in Elixir. One way to do it is using the case block. The case block allows you to specify multiple possible match clauses for a given expression or value. Here we have a bunch of patterns. First, we pattern match on the exact string hello. On the second pattern, we have a 2-element size tuple. On the third pattern match, we have the similar thing we have seen already, head and tail, which head matches on the first argument, first element of the list, and tail holds the rest of the elements. It's a really easy way to verify that we have a non-empty list, because an empty list cannot have a head, right? It doesn't have any elements. Finally, we have a so-called catch-all clause, which basically matches on anything else, anything that hasn't matched already. And here we use a placeholder, but after the underscore we can put a name so that we have some name placeholder, so we know what else do we have there. Pipes are another cool feature of Elixir that allows you to lay out nested calls one after another. Pipes work by passing the value or expression that we have on the left-hand side of the pipe as the first argument of the function on the right side of the pipe. The more nested calls we have, the better it looks when piped. So instead of reading inside out, we can read from left to right. Or even better, from top to bottom. Usually the formatter of Elixir prefers this order, from top to bottom. And since in Elixir everything is an expression, pipes can be used to pass values to case blocks as well. So we can have this composition of functions together. But what do we need to do now if we want to check or we want to debug this pipeline and we want to see what is the value after transform 1? What do we do now? We can easily do that by just adding another pipe with IOInspect, which will just print out this result, and IOInspect will return the value just as it came. So the pipeline itself doesn't change, but we are still debugging our code. As with most functional languages, values in Elixir are immutable, which brings the big benefit of not worrying about mutation of data. Best way to think about Elixir, in my mind, is about variables, is as labels of data. Here, we're labeling this map on the right with the variable mymap. We can pass mymap to the map.pull function and not worry about the value of mymap getting changed. As we can see, if we print out mymap, we will see that the value is just as it was. If we do want to change what mymap points to, although points to, it's not a good way to say it, but what it labels is that we have to rebind it. So if we rebind mymap to the result of map.put, now we can see that we have the result of the function. So just to clarify on this one, variables themselves aren't immutable. The values that they are labeling is, right? Because, for example, in Erlang, you cannot rebind values. You have to just add ones or zeros at the end because they're constants. Elixir makes it a little bit easier for us to make this possible, even though sometimes we don't really want to rebind to the same variable because it could be confusing and it could lead to bugs. And finally, to some of the important stuff. The Erlang VM was designed for massive concurrency, which is why Elixir processes are extremely lightweight. They're not OS processes, nor they're OS threads. Each Elixir process has a very small memory footprint, which allows it to grow and shrink dynamically. A process is created and terminated extremely fast, which is why we can have or even millions of processes running at the same time. And a process can execute some piece of code and terminate. And it can also live forever. Processes don't have any internal concurrency. So the code that runs inside a process runs sequentially. Think of it as a bunch of instructions that run one after another, which means that a process is only doing one thing at a time at any given moment. So in order to run concurrent Elixir code, we need to run multiple processes. There's different ways of starting a process, but the most fundamental one is the spawn function, which takes an anonymous function as an argument, and spawn will start or spawn a process, and it will execute that given anonymous function inside that process. Spawn is a non-blocking function, so after being called, code execution in the parent process continues. At this point in time, we have two completely separate processes running concurrently. They can be just as simple as taking some input and providing some output. You can even think of them as two separate programs. And when I say separate, I mean fully independent. They have nothing in common with each other. Processes have their own separate execution flow, their own memory space, stack, heap. They're separately garbage collected at different points in time. So they are in fact completely separate programs. With microservices, you have a similar idea. Completely independent programs that communicate with each other using some form of messaging protocol. Usually, we'll see that would be HTTP. And Elixir processes are similar in that way. They communicate with each other via messages. That's where message passing comes into play. In order for one process to send some piece of information to another process, it must send a message that contains that data. One way to do that is via the send function, which takes a process ID and a message, where the process ID is the target, the recipient of the message, and the message itself is the data that we want to send, any arbitrary term that we can construct in Elixir. On the other end, the receiver process can use the received block to catch or read one message. The received block is similar to the case block, which we saw earlier. You can specify multiple patterns for incoming messages to distinguish them from one another and handle them accordingly. Sending messages happens asynchronously. When send is called, it only acknowledges that the message has been sent, which means that multiple processes can send messages to the same recipient process at the same time. All these messages that are sent to a particular process end up in the so-called message box of the recipient process, or mailbox. The mailbox is a FIFO queue where messages live. Each process has its own mailbox. This is why there's no problem for multiple processes to send messages to the same process at the same time. All of these messages are going to be queued in this mailbox of the receiver process. And since the mailbox is a queue, messages are usually handled based on arrival. They stay in the mailbox until they are read. Processes don't automatically read messages from the mailbox. As we said already, processes can read one message from the mailbox using the received block. Choosing which message to read comes down to the order of messages in the queue and the pattern that has been specified in the received block. When the received is called, it will try to match on the first message that we have in the mailbox. Here with the yellow outline that we can barely see, we show that we are attempting a pattern match on the first message. If that message matches the pattern, it gets pulled out of the queue and gets handled. Currently in the example, we're matching on a variable, which is considered a wildcard. It can match on anything, right? So what if we want to match on something that is a little bit more specific? Here we have a pattern that expects the message to be a 2-element size tuple, where the first element is the atom OK. I haven't spoken about atoms thus far, but consider them a constant where their value is equal to their name. The received block will start from the first message in the mailbox, as before, and we'll try to match it against the pattern. If that message fails to match the pattern, the process will just move to the next message in the queue. The next message will attempt to match the pattern. Let's say that message it gets pulled out of the queue and gets handled. If that match didn't occur, the receiver would have continued to read or match all of the messages in the queue, in the mailbox, and try to match them against the given pattern. If it goes through all of the messages in the mailbox and none of them match the pattern, the process will block and will wait for a message that matches the pattern arrives in the mailbox. In short, this is how communication between processes works in Elixir. Asynchronous sending of messages and reading messages through pattern match. Another important component of Elixir's good concurrency model is how processes are being scheduled. Again, we had a few words about this earlier, but the scheduler is which takes this important role. Each process job is queued in the run queue, and the scheduler's job is to provide time execution for each of the processes that we have in the run queue. A cooperative scheduler, in cooperative schedulers, when a process is taken for execution, the scheduler will pull out the first process in the queue and give it some time execution. And this time execution is going to be there until the process either finishes or yields control back to the scheduler. When the process that has been scheduled finishes, we can pull the next process from the queue. But what will happen if that process enters an endless loop or takes an absurd amount of time to finish? Well, nothing will happen. And that's kind of the problem. This process essentially blocks the system because it either hasn't finished or it hasn't returned control back to the scheduler. Either way, it's kind of obvious that schedulers are not suitable for a concurrent system. In contrast, a preemptive scheduler, which is the one that is used by the Beam, always tries to give fair share of execution time for each of the processes in the run queue. So if a process takes too much time to finish, the scheduler will just suspend this process, push it to the back of the queue, and give the next process in line his fair share of execution time. So here the long-running task is getting pushed to the back, the next process comes in line. This means that a bad process cannot tank the whole system just because it has entered some bad state. Everything else will kind of run as if nothing bad is happening. Of course, this is just a basic overview of what the Beam scheduler does, but it's what gives Beam languages their concurrency model. This meme kind of tries to summarize the two schedulers. And of course, this doesn't mean that cooperative schedulers are bad. It means that they haven't been designed with concurrency in mind. Now that we know how concurrency on the Beam works, in order to have parallel execution, the Erlang VM, or the Beam, only needs to run multiple schedulers. And it so happens that it does. By default, Beam runs a scheduler for each CPU core on our machine. So a 4-core machine would have 4 schedulers running in parallel, allowing for parallel execution of processes. And while I don't take credit for this diagram, I do like how it represents a top-level view of an Elixir node. And all of this Beam infrastructure lives on a single OS process where our Elixir application runs. But having so many processes running at the same time, it is inevitable that some of them crash or produce errors. So how does Elixir deal with errors, and why is it so well known for its fault tolerance? And I'll try to explain this with a simple analogy. When a hardware device doesn't behave as expected, what is the most usual advice that we give? Have you tried turning it off and on again, right? Well, Elixir takes the same approach when it comes to failed processes. It all comes down to supervisors. And supervisors are a process, just like any other, which main job is to look over or supervise other processes, usually called child processes. To do so, supervisors manage the whole life cycle of their child process, including startup and shutdown. If any of these child processes dies, it's the supervisor's responsibility to restart that process, hoping that this will resolve the issue. Since supervisors are just another process, they can supervise other supervisors, right? Which then creates this so-called supervision tree. Basically, the supervision tree describes the structure of an Elixir application. It creates this hierarchy of processes where we have supervisor process and worker process. And worker processes are usually the process where basically we run our code. The small number that you might be able to see represents the starting order of all the processes in the system. When a supervisor starts a process, if that process happens to be a supervisor, it will wait for the child supervisor to start all of its children, and only then will the parent supervisor continue to his next child. Rickard had an interesting, really good way of presenting this, where he showed that if a supervisor starts a supervisor, it will wait for that supervisor to start its children so that the parent supervisor can continue with his own. If a process dies, his direct parent supervisor is responsible for restarting it. In this scenario, that would be the one outlined with yellow. the crash process gets restarted with a known working state, which is the startup states of that process. If there is a situation, though, where the process dies too many times for a set period of time, the system determines that the restart strategy of the parent process is not cutting it. So it decides to shut down a bigger portion of the whole system in hopes that it will resolve the issue by restarting more processes. This happens by propagating the error of the hierarchy. Right? So the parent supervisor dies, alongside him all of his children, and the error propagates until it reaches another supervisor, which will restart its children based on its given restart strategy. One by one, all processes get restarted, until the whole supervision tree is up and running again. The whole idea behind supervisors is to let process crash and restart them with a non-working state, hence let it crash, hoping that by restarting the process, the issue is going to be resolved. But what if the whole server dies? Well, this is where distribution comes into play, and Beam languages are set up for distribution from the get-go. The main tools for a distributed Elixir system are processes and messages, because processes are completely isolated from each other and communicate through messages. A concurrent system can already be considered a distributed one. And PIDs, which are the unique identifiers of processes, are unique across nodes. So calling a process, we don't care whether the process is running on our current system or on a remote machine or a remote Beam instance. I used this picture earlier to describe how an Elixir system looks like. All these orange boxes are processes that communicate with each other via messages. And adding another Elixir node wouldn't change much of how all this works. So this is how a distributed Elixir system might look like, where each Beam instance is running on a different machine. This is another meme that tries to describe how distributed system kind of work in Elixir. Finally, here are the takeaways. First, their immutability. Once you get comfortable with it, you really don't want to go back. It kind of goes hand in hand with the functional nature of the language. Second, the way processes work and communicate with each other only brings the benefits of what microservices offer and none of the downsides. Third, you get high concurrency and parallelism out of the box, which means that it's perfect for high user load applications. Fourth, the fault tolerance is managed by Supervision tree and allows you to not write defensive programming while being confident that your application is going to be stable. Let's face it, bugs are inevitable. So instead of trying to avoid them, I think it's better for how the system handles them when they happen. Finally, we get distribution by design, which allows for horizontal scaling and a resilient application. I'm really hoping that this is how you're feeling right now. Or maybe like this. I don't know, pick your meme. Don't start running and trying to push Elixir everywhere, because it doesn't happen so easy. And then you might think, okay, how can I convince people, right? Again, it's not that easy, even though it sounds amazing to us.
Thank you.